Okay, so today we are going to discuss the same chapter. We will continue diffraction. Little bit more theoretical points we will discuss, and then we'll move forward. Okay, so let us note some points related with diffraction. Diffraction. So, what is diffraction of light? What is diffraction of light? The phenomena of bending the phenomena of bending of light around the corners of an obstacle or aperture of the size of the wavelength of light is called diffraction. So technically you can explain this with this definition. What is diffraction? So it is the bending of light around the corners, okay, right, of an obstacle or aperture of the size. This condition is important. Size of the object is nearly equal to the wavelength of the light. Let's take example. Suppose, for example, there is a aperture like this here, and let us consider that the wavefronts are coming. Wavefronts. So these wavefronts, which we can see here, these wavefronts are getting exposed here like this. So each point on the wavefront emits their own secondary wavelets like this. So they will be emitting wavefronts like this. So you can see that the waves can go this side also. It can bend here also. So although the obstacle is limited here only, this is the obstacle. This is an obstacle here. I have taken example of an obstacle here. This is an obstacle. So ray of light which is coming here, I have taken a point source. Suppose this is a point source of light. So the wavefronts are coming like this. Spherical wavefronts are coming like this. So as this spherical wavefront is hitting here to this surface, what happens? Each point on this is behaving like a source, and now they started emitting the wavefronts like this. So wavefront is going to go beyond this region also. So that means the light can go here also. Light is able to reach these directions, these places also. Light is able to reach. So how light is able to bend around the corner? This is the corner, right? Around the corner it is able to bend. That is process is called diffraction. So how it is able to bend? It is not that in all cases it will bend. It is bending because this obstacle size is compared to the wavelength. It is almost similar to the wavelength of light. Suppose wavelength of light, if you take light from 400 nanometer or 350 nanometer to 700 nanometer nearly, so this object also, or this obstacle should also have similar size, maybe nearly the same as the wavelength of the light. So this effect we can see, diffraction effect is happening because of that only. Okay, and if you take these slits like aperture means that single slit. Now see this single slit. So in single slit, suppose if I consider this light is coming like this way. If I take point source means this is like the wavefront, and now each point on this is getting exposed, so each point on this behaves like a source. Each point behaves like a source, so they are going to emit their wavefront here like this. Everywhere it will go beyond the corners, like this, around the corner. That's how. And if you can keep a screen here, you can keep a screen, so each point will be sending its wavefront. So any point on the screen, if you see any point, these light rays which will be coming from these points, these light rays from different points can come, and they can have superposition. That's what we have discussed in Young's single slit experiment, how interference patterns are forming at any point on the screen. Right, so that is what it is. Let us note some more theoretical points related to that. First point we have already noted previously, point that we noted, that's the first point. Second point we are going to note the phenomena resulting the phenomena resulting from the superposition of of secondary wavelets. That's what important. Secondary wavelets originating 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 from different parts of the same wavefront of the same wavefront same wavefront is defined as diffraction of light. Diffraction of light. Now here you can clearly see why they are saying the same wavefront, because in the previous diagram, if you see here, this wavefront, if you see this wavefront, this is the wavefront. Now each of these secondary wavelets are coming from the same wavefront. So these rays are coming from the secondary wavelets which are coming from the same wavefront. That is why this is called diffraction. Very important definition, because if you take a single slit and double slit, that's the main difference, because in double slit they are two different wavefront, but in single slit only one wavefront, and those secondary wavelets are only acting as sources. Very important definition. Okay. Okay. Diffraction diffraction is the characteristics of all types of waves. All types of waves, not only this light wave, sound wave, or any wave you take, diffraction happens in all those types of waves. Next point, greater greater the wavelength, greater the wavelength lambda of wave, greater the wavelength of wave, higher higher will be its degree of diffraction. So that means if wavelengths are more, then it will have more chances of having diffraction. That's the idea. Why? Why? It is because if wavefront is means large wavefront will be there, more wavelength will be there, then there will be more secondary wavelets will be emitting the waves, which will cause the superposition. That's the reason. Okay. Now let us discuss the types of diffraction. Types of diffraction. Types of diffraction. First type, it is called Fresnel diffraction. What happens in Fresnel diffraction? If source or screen or both are at finite distance from the diffracting device, okay, that is what it is. The source or obstacle, source or screen, you can say, source or screen or both are at finite distance, finite distance from the diffracting device. That means obstacle or aperture. That's what it is. Fresnel diffraction means the source or the screen both are finite distance. Let's see the example. Here examples are also given. What are the examples of this? Diffraction, diffraction at a straight edge, diffraction at a straight edge, narrow wire, narrow wire, or small opaque disk, small opaque disk, etc. These are examples. Let's note the diagram of this. So suppose if I draw one's opening or slits like this and assume that there is a point source of light which is sending light in all possible directions. So wavefront of course will be coming like this way, but wavefront will be coming like this. So here this wavefront will be getting, some portion will get trapped here. Discuss that. So light rays will be going here in all directions like this. Now here also will be going in all possible directions, and you can put a screen here. This is the source. So source and screen are finite distance from this aperture or from this opening. So these distances are finite. Finite. These distances are also finite. So this type of diffraction pattern that is happening, that is called Fresnel diffraction. Very important. Then we will discuss. But Fresnel diffraction questions generally they don't give. But in board exam or other places they can give you to draw the diagram, examples, so that we can do it. Okay, then let us go into Fraunhofer, which is the second type. Fraunhofer is what we have discussed. Fraunhofer. Fraunhofer. Fraunhofer diffraction. So what happens in this case? The source and screen are effectively at large distance or infinite distance. The source or screen are effectively at infinite distance from the diffracting device, from the diffracting device. Example, what are examples of that? Diffraction at single slit, diffraction at single slit, double slit, and diffraction grating. These are examples of that. Okay, let us see the diagram of this. Infinite means rays will become parallel rays. So suppose if we have single slit and the rays of lights are coming parallel, parallel rays, you can say that the source is at infinity. Then this side you can keep a lens. Sometimes lens can be kept here. Then this rays will be merging at some point. Right. So here on this screen, this can be formed. Right. So the wavefront, we want to show wavefront are perpendicular wavefronts like this. So this is what is the device, single slit. Okay, that's what it is. Here the rays are coming from infinity, so it is parallel rays. That is Fraunhofer diffraction. By the way, this name is important because once my professor was telling to join Fraunhofer Institute in Germany. He was sending me. I told no, I don't want to do. They are sending in Fraunhofer. There is a Fraunhofer Institute there. Okay, in Germany for some work, project work, some project work. So I did not want to go. So we want to send on some projects for working for few months there. But I told no, no. For me, my PhD work itself is so much now. So how can I do one for project work? What reason behind? Reason behind is um, it's interest. Suppose you are doing something and then you don't like, then you change. There should not be any obligation that you have to do only one thing. Right? You should be free to do whatever you like. Suppose now I am teaching, I am liking teaching. Suppose I don't like teaching, then I will go somewhere else, I will do something else. Whichever I will like, I will do. Society has made us to do something and they are expecting to do same thing. They want us to study for so many years, after studying, suppose you are going to study medical. So after doing 5 years MBBS, you are supposed to work as a doctor only. You should not do anything else. People will say if you do some business, suppose you want to fed up with that, I don't want to do doctor, I want to do some business. They will not like it. People will not say, then why you have wasted so much 5 years? But they don't understand that all these are learning only. 5 years you have not wasted. 5 years you have invested it. You learn something, now you find it useful and you like it, so you do it. Right? But suppose after doing 5 years you want to do music, then you go learn music and do whatever. Society should be free, right? People should give freedom to everybody. But nowadays they are expecting like that only. Why it is like that? I don't know. They should give freedom to everybody. Whatever they like, they should do. Right now, it's not that I have wasted. I learned. I learned something, and then whatever I found useful, I do. Then which I do not find useful, I don't do. Because things can change. Nature is changing. Everything is changing. Why not we should change? Why we should? So, but still, I find that many doctors also do many things beside doing things. Some doctors are also musicians. Yeah, some doctors are musicians. Some doctors are artists. Some doctor. It is not the doctor may be their side profession, but they can do something else. And once if they feel that I should do something, they feel so much, then they can leave the profession also, right? It's not that for money only we have to do it, but for society they expect that you have to do for money only. That is what they think, right? Money is okay. Money you can do earn by something else also, na? Right? That is the second thing. People think like that. Okay. So once I was doing PhD, but then and I left, then many people told, why are you doing like this? Why? But they think that I cannot live without that. That is not true. I can do a farming also and I can live with farming. Huh? Or I can do any small work also, I can live with that. But the thing is that people make an expectation of you. People make an expectation from you and they want that you should fulfill that expectation. That is not good. Now, why we should do like that? Let them live freely. Huh? Like that also, with parents also, they expect children that you should do this only, right? But actually, it is not a maturity. Maturity is to live. Let them live freely. God has given everybody freedom. Let them enjoy their freedom. That's what it is. People they don't understand these things, right? Okay. So let us go further in this. Okay, so this is what it is from how far it is. Then let us go next. Afterwards, what else? Single slit diffraction already we have discussed all formulas we have discussed, right? Now resolving power, although it is not in your syllabus, means they have not put it, but maybe in future they can keep it. So we can discuss little bit. Resolving power is not that much. Okay, very small topic is there. In NCERT it is given by the way, but let us cover that. Resolving power. Resolving power. Resolving power of optical instruments. Optical instruments. Okay, so suppose first of all we assume that there is a lens like this. Because any optical instrument like microscope, compound microscope, simple microscope, telescope, it is made up of convex lenses. So let us say that this is the size, aperture size 2A of this, right? And let us consider that here we are keeping this screen. The screen we are keeping, and this distance D we are choosing as focus. So what happens when rays are coming? Images will be formed. Actually, this lens is going to act as a diffracting device. It's going to act as a slit. Okay, slit. The size of the slit that we write as B, right? Slit width is B. That we are taking as 2A, and then light is going to diffract, and the maximum minimum will be forming. And we already know that a central maxima is there here. Central maxima is forming here. This is the central maxima, and then secondary maximas are also forming like this way. Secondary maximas also form, right? So now here, this yesterday we have discussed that the radius of the bright spot, right? So on the screen, when you see here, this is a very nice diagram given in NCRT that this will look like a bright spot like this. Okay. This is the bright spot, and if you go for the other minimas, then you may also find some thin ring-like pattern. Maybe instead of like this, some kind of pattern like that we can we can find. But this is the main bright spot here. This bright spot. That's the main bright spot. Then another will be dark. Then again bright spot we will see here, like this kind of pattern will be followed on this tree. Okay, like this. Now here already we have done the calculation, but now here by experimental we will see that this radius already we have calculated. If you remember, by diffraction we have calculated this radius or not. Previously we have done diffraction and this was lambda d by b. That was the formula for radius of this first bright spot. But according to experiments, this radius is coming as 0.61 lambda f by a here according to this. So if I go with this experimental fact, then this radius r naught is of course nearly 1 we write here, but here according to experiment 1.22 lambda d by b it comes. Now if you substitute 1.22 lambda b is to a, so you will get this as 0.61 lambda d by a. That's the radius of the bright spot. So this thing we have to note first. Okay, then so that means if you keep a lens, then lens will show diffraction effect, and the radius of the bright spot which will be forming is given by this factor. Although we can say theoretically it is 1 lambda d by d, but a factor of 1.22 factor comes because of some experimental or circular aperture. Aperture is now different because this is not exactly a slit. First of all, this lens is not a slit because we have derived this formula for slit, but for the shape of this lens 1.22 factor comes in NCERT. That's what it is given. So according to that we can calculate radius. It comes like this, 0.61 lambda f by a. A is the aperture radius of this lens. Okay. Now coming to resolving power, how do we calculate resolving power? It's a very interesting thing. Resolving power, how do we calculate? So suppose that this is the lens. This is the lens, and let us consider that there is an object here. Let us consider object, and there is a string here. So if this object, if I consider and I take a ray coming like this way to the uh, aperture of this, okay, this angle is going to be beta. Let us call this angle beta, and let us keep this object at the focus of this. Object is kept at the focus, and then aperture size, of course we are calling this distance as small b. Let us call this distance as b. Then what happens is we will have like the same way we discussed that bright spot will be forming. This is what is bright spot, and radius of bright spot, diameter of bright spot is 2 times, so that is what is 1.22 lambda 1.22 lambda d by a. So how do we calculate that? Okay, let us see that how much it will come. So first consider this is object distance, then this is the image distance v. This v we can take as capital D, and here the angular position of this is like the half angular position theta, right? And the image which is formed like a spot because of this diffraction thing. Now here we need to note that the minimum distance between the object d minimum is equal to 1.22 lambda by 2 times refractive index n into sine of beta. How they are deriving? that is not given, but they have written it like this. So let us just write it here. Hmm. Derivation is also not in the scope of this. But something we can understand from it what the minimum it is. They are saying that the images which are getting formed should be clearly resolved. That means, suppose these images which are formed, these images should form as a spot. So for clear resolution, these images should be at a minimum distance. This minimum distance between them. Okay, this is the minimum distance between them. Okay. So this minimum distance is given as 1.22 lambda by 2, and I think here this they are taking the size of the aperture based on this. How are they taking side of aperture? Because sine beta is what, perpendicular by hypotenuse, or it is like tan only. So this distance 1.22 lambda by d, I think they are taking this as the focal length also. Might be that. So focal length sine beta, because if I say for example 1.22 lambda d by b, that was formula. B was what? B was this distance. So this distance, if I want to write, I can write in terms of focal length also, isn't it? D. Suppose if I consider the image forming, so then D I have to take as focal length. B I can write in terms of that. Maybe that is what they are doing here. D if I take as focal length, then 1.22 lambda f by B. This B we can write as 2 times of this distance, and this distance can be written as f uh, tan theta, f tan beta, f tan beta. So then ff can be cancelled. 1.22 lambda by 2. Tan beta is same as sin beta. And this factor n, it is coming because of refractive index. Right? Refractive index. Or light may be traveling in this medium, so they are taking as the optical path. I think yes, that's what is the derivation it is. Hmm. This is also focal length, and that is also focal length. They are keeping object here. Okay. So these are some derivations based in NCRT, what they are considering here. Right? This derivation. So we should note down this formula. So this size, what they are writing here, that size, that is this distance is 1.22 lambda f by d. There, okay. F by d. Here d means f by b here. Okay. How are they getting that total length? Again, I told no. This minimum is 1.22 lambda d by b. D they are choosing as focal length here. The same dimension d is equal to focal length. So that becomes 1.22 lambda f by b. That's what it is. Okay. Now, so this distance, what is this distance? The resolving power. So note down the final point on this notice. Note this: the resolving power, the resolving power of microscope is given by the reciprocal of the minimum separation of 2 points seen as distinct. So I think the resolving power is defined as resolving power is defined as 1 by reciprocal of that given 1 by d minimum. Yes, I think this is what it is. So it will become uh, 2 n sine beta by 1.22 lambda. That's the formula for resolving power. So resolving power is more if refractive index. I think this refractive index is nothing but the medium refractive index in which lenses are there. Sometimes lenses can be kept in a different refractive index object and this, right? So this refractive index is n. So sometimes liquids of different medium are used, so we can use that. Okay. So you can increase this resolving power by changing the refractive index here, refractive index, and beta also the aperture size can be increased. Okay, lambda is wavelength. If you use smaller wavelength, then we can go for that. Okay, that's what it is. I think that's all it is. Then last topic in this before we go into polarization is the validity of ray optics. Validity of wave optics. That is given by Fresnel distance. Fresnel distance. Fresnel distance ZF is equal to A square by lambda. A square by lambda. How actually this idea comes? Fresnel distance. I'll try to give, although it is not given in NCERT, but I think I have seen idea behind Fresnel distance. So suppose if you take a slit here, and this slit width is B, B is the width of the slit, and you are thinking here. So suppose if these rays are coming, let us take, we are taking rays like this, and these rays are uh, making some spot here, and this distance is d. Let us call it as d. Right. So this is bright spot. We know already this distance is equal to bright spot lambda d by d. Right. Lambda d by d. So this d, I think this d we are going to call it as Fresnel distance z. Fresnel distance. Okay. We are going to call this as Fresnel distance. So if this um, distance lambda d by b d, b or a here, I think it is the same thing. You may call b as a. Let's call b as a. So if I consider this width, this whole size or aperture opening, this aperture opening, if this become equal to half the radius, then that Fresnel distance is defined as that. Okay, so suppose if I consider this opening B equal to lambda d by b, then what will be d? D becomes b square by lambda. This d is what is called as Fresnel distance. Fresnel distance, and this is b, means here we are taking a, b is equal to a square by lambda. So what is a here? A is the size of the object, and lambda is wavelength of object, and zf is the Fresnel distance. What is the meaning of Fresnel distance? Means suppose there is no pattern is forming, no maximum minimum is forming, so this light is directly projecting there, right? So if this becomes equal to this, then wave phenomena will not be happening. Okay, that is the idea behind Fresnel distance. So for distances, now note here, for distances, for distances smaller than, much smaller than, much smaller than Fresnel distance, the spreading due to diffraction is smaller compared to size of the thing. Okay. That means if you go distance lesser than that, then the spreading of diffraction pattern does not happen much. Okay, it becomes comparable when the distance is approximately this. It becomes comparable if it becomes comparable when distance is equal to fractional distance. And what happens if it is greater than for distance greater than fractional distance? Spreading due to diffraction dominates over the for distance greater than fractional distance, spreading due to diffraction dominates dominates over that due to ray optics. Ray optics. That is the size of the aperture. Let's understand this more. Okay, so suppose you calculate the Fresnel distance. Okay, Fresnel distance. And suppose the Fresnel distance, suppose for example this the aperture size is very large as compared to the wavelength, then this will be coming very large. So very large distance means what? Suppose some value of ZF you got. So for distances smaller than ZF, if you get distances smaller than that, the spreading due to diffraction is smaller compared to the size. So diffraction will not be visible. That's what is the idea. Okay, for distances smaller than ZF, the spreading due to diffraction is smaller compared to the size of the beam. It becomes comparable when distance is equal to this. So if the distance is equal to this, then there will be wave phenomena will be happening. For distance greater than this, spreading due to diffraction dominates over that due to. So if you go distance greater than this, uh, this phenomena of wave optics will happen. Distance equal to or less than this, ray optics phenomena will happen. That is the idea here. Okay, and in NCRT, some examples are also given. With that, things will become clear. So last topic, let us go into the polarization, and with polarization we will be finding this chapter. Okay, so done. I think this chapter is almost going to get over now. Today we'll finish up this chapter. Polarization. Polarization of light. So note that polarization happens only for transverse wave. Only transverse wave shows polarization effect. Polarization does not happen in longitudinal. So first let us understand the setup of polarization. Polarization, did you finish in class, Sam? Let us note polarization means. So note that in electromagnetic waves, that means light, this formula for magnetic field amplitude is electric field by C. You remember this formula, EMW. So C is very large. So this is very small than E naught. Okay, right. So light wave can be simply simply represented simply represented by oscillation of electric field. So although this uh, is made up of both electric field and magnetic field, right? Because light is an electromagnetic wave, right? Light is electromagnetic wave which is made up of both electric field and magnetic field oscillating. But because the magnetic field is very small as compared to electric field, we can just represent light wave as oscillation of electric field, right? Now let us understand what is called unpolarized light. Unpolarized, unpolarized light. So light from sun or bulb, etc. These lights are called unpolarized light. Why? Because electric field vectors, electric field vectors are distributed in all directions in all directions perpendicular perpendicular to the direction of direction of propagation of light. So that is what is the meaning of unpolarized light. So if the electric field vectors are distributed in all directions perpendicular to that, that is called unpolarized light. For example, suppose if I am showing a, let us say light is traveling in this direction. This is the direction of propagation. Propagation. So if I consider a plane here, this plane is a plane which is perpendicular to this. Now in this plane, electric field can vibrate or oscillate in any directions. This way, this way, this way. All random directions you can say. Random direction of electric field oscillation. But definitely in this plane, we can resolve the vector into two components, right? One, this is a perpendicular. Note that this plane itself is perpendicular to this. This is like x-axis, so this is yz plane. In this yz plane, I can resolve into two directions which are perpendicular to each other. So we can resolve always in these two directions. Because any vector in a plane can be resolved along x-axis and y-axis. So these are two different perpendicular directions, right? So you may represent one as horizontal, another as vertical. Now this is very important. So I am going to represent this as one vertical and another as horizontal. Because from this direction, if I am going to see this direction, I am seeing this, and these are two perpendicular directions. So if I consider this direction and this direction, and we are looking from this direction, so one of them will look like dot. Let us represent one of them as green. This is green. So green will look like dot, and this blue color, that you can represent it like this line. Okay, like this. So this will represent vertical, This represent vertical oscillation, vertical oscillation, and this green color represent horizontal oscillation, horizontal, horizontal oscillation, vertical and horizontal oscillations. Okay, this is what is unpolarized light. So unpolarized light can be represented by this type of line with a dot here. Dot represent this way horizontal, and this vertical line this represent vertical oscillation. So that means it's a unpolarized light. This is representing unpolarized light. Unpolarized light. But in some textbook they may also represent it simply like this diagram. This diagram which is showing in all possible directions, right? This direction, all possible directions. That way also you can represent. But sometimes many textbook we represent it like this way. Both diagram can be used to represent unpolarized light. Okay. Then what is polarized light? Let us know polarized light. Polarized, polarized light. Polarized light. The phenomena of limiting, phenomena of limiting the oscillation of electric field in one direction, in one direction, in a plane, in a plane perpendicular, perpendicular to the direction, to the direction of propagation, to the direction of propagation of light wave is called polarization, polarization of light. So what is called polarization of light we can understand from this definition. So here it is random vibration, but suppose if you, of course the ray is going in perpendicular direction, so perpendicular to that, if we can keep, if we can take a plane which is perpendicular, like for example here horizontal and vertical, we have seen that. So horizontal and vertical, if we see, then we can, I think time is over, huh? But he is joining. What time? 10:15. I okay. I think he's waiting. Okay, so let us quickly finish this. So I'll tell him to wait. I'll tell him to wait for 2 minutes. I will just please wait few minutes. Okay, I'm just winding up this topic. Right. So this is what is polarization of light. So polarization of light means if you limit, for example, suppose this is unpolarized light, and after passing through some material, it becomes like this, or it becomes like this. Vibration is only happening in vertical or horizontal. So this type of light representation, it is called plane polarized, plane polarized, plane polarized, or it is also called linearly polarized, linearly polarized, linearly polarized light. So what is the law here? Now here I will briefly give, quickly I'll give this law, one law that is called Malus law. What happens in Malus law is that there are some substances called polarizer which has one axis. This is the axis. This is called pass axis, and these are called polarizer. So if I am sending a unpolarized light, first of all, this is a unpolarized light. Let us say its intensity is I naught. After passing through a polarizer, it will oscillate in this direction only, and this intensity will become I naught by 2. First of all, this will become half. Okay, this is one. So, what is Malus law? That also we'll discuss, but first we need to note this. Then, suppose if there is a polarized light is coming, let us say I1 in this direction, and this is the axis of the polarizer. This is the pass axis, and this angle is theta. So, after passing through this intensity becomes I1 cos squared theta. Okay, why it happens? Because suppose this amplitude is A1, this amplitude is A0, so here the component of amplitude you have to take as A1 cos theta. So you know intensity is proportional to the amplitude square, so this A1 I1 is proportional to A1 square, and this intensity is proportional to square of this, that's why it become I1 cos square theta. This law is called Malus law. Okay, this is called Malus law. Malus law. And note that here why it has become half, because angle we have to take a 45 degree because it is in random direction. Random direction means average value. So anyway you can understand average value of cos square is half. That's why half it is coming factor. That's the definition. Okay. So most of the question will be working based on this. And another thing is about the Brewster law. Brewster law. Brewester's law. Brewster's law talks about the polarization happening due to reflection. Okay. So what happens here? Suppose a light is coming, and this light is completely unpolarized. Unpolarized light. Unpolarized. Now, when reflection happens at this point, you can draw normal. So both the things can happen. Both reflection can also happen, and reflection can also happen. So polarization, how will polarization happens in this case? Okay. So what happens that the reflected light comes here. This reflected light is completely plane polarized. Plane polarized. Reflected reflected light. It's plane polarized, and this refracted light. This is refracted light. This refracted light is partially polarized. Partially polarized. Okay. So partially polarized, how do you represent partially polarized? Partially plane polarized you can represent as dot dot dot. Partially polarized you can represent like this, and a small dot you can represent like this. This is partially polarized. Okay. And here this angle between this reflected that becomes 90 degree, and this angle I, this is also I only, and this is angle of reflection R. Okay, and this is mu, outside it's air, so 1, so applies Snell's law. So 1 into sine I is equal to mu into sine of R. Note here that this total angle is 180 degrees, so I plus 90 plus R becomes 180 degrees, so R becomes 90 minus I. So if you put this here, mu sine 90 minus I, that becomes mu cos I sin I. So that becomes tan I is equal to mu. This I is called tan inverse mu. This is called polarization from polarizing angle. This is called polarizing angle or Brewster angle. Polarizing angle or Brewster angle. Brewster's angle. Okay, and this is what is called Brevester's law. Brevester's law says that if light is going from rarer to denser medium, and if polarization happens, the reflected and refracted rays become perpendicular, right? And we got the angle I formula is tan inverse of mu. That's what it is. So with this, we are going to wind up this. Okay. So this chapter is done. Now you can start working question. Further, we can go more detail afterwards, but that is right now sufficient to work out problems on this subject. Fine. Right? So then we will take up further in the next. So uh, let me stop that, and again I will start it.